Hello, my name is Reese Bailey, and for this presentation I will be presenting the investigation of ballast degradation and fouling and the application of ground-penetrating radar monitoring. Railroads are a fundamental means of transport for a range of users. It is a fixed structure which provides a guided route for a number of traffic opportunities. However, as with any structure, a railroad will deteriorate over time, resulting from environmental, chemical, and various loading effects. Therefore, a railroad section will require ongoing maintenance to ensure that the standard requirements are met. There are several methods of monitoring that have been implemented within the railway industry to identify degradation, which are critical for the planning of maintenance. The objectives of this study were to investigate the traditional management of ballast degradation currently being operated, to draw conclusions on how future management systems may utilize the application of GPR monitoring to better the approach to the issue. Specifically looking at ballasted track, this study will delve into the history and methodology of the most common forms of track substructure management to aid in the explanation and investigation of ballast management. Looking at the track structure, specifically ballast track, can be broken down into two components, each consisting of several subcomponents. The superstructure typically consists of rail, fasteners and sleepers, whereas the substructure consists of the ballast, capping layer, formation and subgrade. The purpose of the substructure is to restrain, resist and distribute the loads resulting from rail traffic. The structure transfers the loads through the rail to the sleepers, through the ballast bed and to the formation. The track structure is subject to three load categories, which include vertical loads, longitudinal loads and lateral loads. The vertical loads that the track is subject to are all forces which are applied perpendicular to the rail. As seen in the figure to the right, the rail is subject to two types of vertical forces, the negative wheel force and the positive uplift force. As the load is applied to the rail, the forces through the structure distribute, increasing the load footprint on each consecutive layer. The ballast bed is the uppermost layer of the substructure, providing total support of the sleepers and the loads that are distributed through them. The granular material that makes up ballast consists of like-sized aggregate with a normal size of approximately 60 mm. Each of the aggregate particles consists of coarse angular edges, free from dust and dirt. Due to the variety of materials which have been used throughout the industry, the characteristics can considerably vary, which is why this is still a subject of investigation. A common method used to ensure the quality of ballast is through grading. The following table to the right presents the requirements as outlined by the Australian Rail Track Corporation. This method utilises a series of sieves which determine the sufficient grade of the aggregate. The ballast material must be both strong and durable, capable of withstanding the cycle loads it will experience. New ballast materials must undergo a series of tests to ensure that they exceed the load capacities. To effectively design the ballast bed, it is vital to know the traffic tasks it will encounter. The thickness of the ballast should be determined as a result of the maximum stress at the interfaces, acceptable bearing pressure of the underlying layers, and the stress distribution through the body of the ballast. The stresses that the ballast particles are subject to consequently result in plastic deformation and degradation. The combination of these variations within the ballast result in instabilities of the substructure. The deformation and degradation results in particles to lose their relatively sharp angular finishes, becoming more rounded. This, along with the presence of fines and debris within the voids, causes a reduction in the friction between the ballast particles, resulting in further particle strains. Ballast fouling and degradation have previously been overlooked by the industry. However, in recent times there has become heightened interest to determine the best course of action to manage the ever-prevailing issue. Traditionally, there are several methods of inspection which are used to identify the condition of track ballast. Some of the most common of these include visual inspection, section cuts, windowless sampling, and track recording car inspections. The track recording car is not directly affiliated with ballast monitoring, however it is an instrument which is used to identify the present rail alignment of the track structure. Although this method does not directly identify ballast conditions, it could be used to identify areas where ballast fouling is present due to misalignment of the track. There are several methods that are currently being employed to determine the degree of contamination within a ballast section. Two of these methods, the D-bar and the ballast fouling index, or BFI, are determined through sieve analysis. Percentage voids contaminated, or PVC, is, as the name suggests, the percentage of voids contaminated within a ballast sample. This method of testing is not typically used, as it is difficult and time-consuming to measure the voids within the ballast sample. However, this method of testing has been adopted by ground-penetrating radar applications, as no physical testing is required, using computer modeling to determine the volume. Ground-penetrating radar is an operation that has been developed to utilize the transmission of electromagnetic waves via an antenna into a subsurface. The reflection, refraction, and scattering of these waves from the interface within the subsurface are then received and an image of the data can be formed. Due to its non-intrusive ability to detect material interfaces, it has been increasingly employed within the railway industry in the last decade, capable of producing usable data for an entire network within a short period of time. The primary use of these instruments for the railway application is to identify areas of ballast fouling and the depth of the formation of ballast interface. GPR in the railway utilizes two types of antenna, which have separate purposes. A 2 GHz antenna is used to identify the ballast condition, and a 400 MHz antenna is used to identify the depth of the ballast bed. Track degradation management typically consists of three maintenance methods. These include resurfacing, undercutting, and reconditioning. Resurfacing is the common method used to correct any misalignments to the track geometry. It includes two processes. The first is the realignment of the superstructure to the pre-existing standard alignment. This is followed by the compaction of the ballast beneath the tyres to hold this alignment. Undercutting is the method of removing contaminated ballast from a track structure and replacing with either clean or new, fresh ballast. This process can either be done by an undercutting machine, which is an on-track vehicle, or excavated. Reconditioning is the most extensive method of management, in which the entire track structure is renewed. The method that was undertaken for this investigative analysis began with the isolation of sections with sufficient data. This was followed by gathering all relevant GPR data for both 2011 and 2015 and the maintenance history for 2011 to present for each section under investigation. A comparative analysis was developed to both determine the effects of GPR on maintenance planning and the variation between 2011 and 2015 data sets. This was followed by investigating the rate of contamination for several sections. When first processed, the GPR data produces a radargram image, an example of which can be seen here. The signal from the GPR scatters off the ballast particles in the air voids, creating the different shades in the radargram. These are then interpreted to develop the PVC. This figure shows how this is processed. This is the fully processed data that was presented in PDF format. The two metrics which were used for the investigation were the ballast thickness index and the GPR PVC. These legends detail what the various colours signify. The ballast thickness index was then used to approximate the ballast depth. Sufficient maintenance history needed to be acquired so that a logical comparison could be presented. The maintenance works carried out between 2011 to the present were scheduled through traditional management planning. There were some issues that became relevant during the collection of the maintenance history, such that it was assumed that not all maintenance data was able to be located, and not all data collected were a true reflection of the works carried out. The example shown here displays the GPR data from 2011 mapped against the maintenance history that was able to be retrieved for this particular section, highlighting the expected undercutting scope based off the GPR data and the actual works that were carried out post-GPR. This particular example indicates that there was a large portion of fouled ballast needing undercutting, where only a small portion was done. Using the GPR gathered from 2011 and 2015, the total volume of ballast was found using the standard profiling of the ballast trap. This volume was then multiplied by the PVC to give an approximate volume of fouled ballast. The graphs shown here represent these volumes for the two sections, with the blue line indicating the total volumes and the red the approximate fouled volume. The circled sections are the locations of structures such as bridges and platforms. A number of sections were selected which had no known maintenance between 2011 and 2015 to determine the rate of contamination. For each section, the mega gross tonnage, as well as the change in PVC between the 2011 and 2015 GPR data sets were found. The average change in PVC was determined from 100 meter lengths of each section, disregarding any with less than 50 meters worth of data, and averaged using Minitab. The rate for each length was determined as PVC over 1000 mega gross tons. The table here represents the final rates determined for each section. To conclude, it was found that the application of GPR may potentially be a useful device for future management of degradation and fouling, by aiding in the planning and maintenance of works, identifying approximate volumes of ballast, and identifying the rate of contamination to determine the life expectancy of a particular ballast section. However, it is recommended that further in-depth investigation be carried out to fully understand the validity of GPR applications within the railway industry. Thank you for your attention.